Okay, hello students, welcome to today's lesson on chromatography. We're just looking at how proteins can be analysed by chromatography. Today we'll particularly look at high performance liquid chromatography, and you can see an example of that HPLC setup right here on the front page, and let's get into it. Now if we think about chromatography, we're going to talk about 4 different types of chromatography. First of all, we'll talk about paper chromatography. So typically when we think about paper chromatography or any chromatography, there's a mobile phase, which is the solvent. That's the thing that's moving. The stationary phase is the paper. Now it might also be a thin layer plate in thin layer plate chromatography. The compounds that have to be tested are adsorbed, and that's a chemical attraction, and they're adsorbed by the solvent. Now the paper or the stationary phase absorbs the solvent as it goes, and as the solvent passes up through the ink, for example, it will adsorb and then desorb. Now the mobile phase moves and collects compounds when it moves through that stationary phase. So the mobile phase acts as a solvent in the paper and in thin layer chromatography. A piece of paper is placed in a solvent and that acts as a stationary phase in paper chromatography. So the thin layer cell plays the role of a stationary phase in thin layer chromatography. So these types of chromatography avail capillary action, which is just the ability of liquids to go up small tubes and to travel the solvent via the stationary phase. So you may have done something like this at home or in junior science. Just put some metho in the bottom of a beaker, and we've drawn a line, and we've put some texture marks on that line. And you can see we've got 3 different types of textures here, and they're all black pens, but you can see that black pens are made up of different components. I'm looking at the one particularly on the left. So we've got ethanol or methylated spirits, which is the solvent, and it's absorbed into the stationary phase, which is the paper. Now it's going to be moving up through that paper. Now we put the ink on that origin line, and what's happening is that solvent is adsorbing the inks. Now the different components of the inks will then desorb back onto the paper, which is the stationary phase. Now the component of the ink travels from the origin and then desorbs onto the stationary phase, and then we have the solvent front right up the top. Now we can calculate the retention factor or the retardation factor. Your book and your syllabus call it different things, but essentially they're the RF value. And we're just looking at the distance the component has travelled divided by the solvent front. So if it has a RF value of 1, it's the same distance as the solvent front. And you can see that with that light blue mark on the top left. But if we have a look here at the red one, you can see that that red component of the ink has desorbed about 2/3 of the way up. So it's approximately like 0.7 of an RF value. We'd have to get a ruler out and measure it and calculate it. So the retardation factor or the retention factor, what do we need to know? The more soluble it is, or the greater the RF value, the closer it is to 1. Now, those inks can't go past the solvent front, so it can't go past 1. And the most soluble component is going to be right up the top, closest to the solvent front. So the retention factor is a quantitative indication which tells about the distance travelled by a particular compound in a particular solvent. So the value helps to know that the known compound and an unknown compound are similar or not. So if the value of the RF of a known compound is equal to the RF value of an unknown compound, then it means that the 2 compounds are the same or identical. Now, retention factor is defined as a ratio of the distance travelled by the solute to the distance travelled by the solute front. Now, if we have a look at this diagram here on the left, we've got a lolly, and we want to just compare that to some known sugars. So we know lollies are yummy and they're full of sugar. Let's test which sugars are in the lolly. So we've got two components to this lolly. We've got an A sample and a B sample. Now, if I were to compare that against a known standard of fructose, for example, I can see that, oh yes, that B component is the same as fructose, and the A component is the same as glucose. So I can see that this lolly has both fructose and glucose in it. Now, gas chromatography, we're not going to talk too much about, but essentially we've got a carrier gas like nitrogen. It's inert, and we're going to inject that into the sample, and the sample is vaporized in an oven. So you can see that, oh yeah, it's heated up. Now, the stationary phase must be a solid or a liquid, so it could be beads or something like that. The column is a glass series of loops, about 4 mils of internal diameter. It's about 2 to 3 meters long. As I said, it's vaporized in the oven. Keep it moving as a gas, and then the least soluble components are swept out first. If we have a look at column chromatography, this works on gravity. So we've got a three-dimensional porous column. It's top fed, and the stationary phase is small particles, for example, silica. Now, separated components leave the column at the end, and they are called the eluent. And there's two main examples there of gas chromatography, which we talked about, and high performance liquid chromatography, which we're just about to talk about now. So if we look at HPLC, the mobile phase is under pressure, so it's pushing it through. The retention time now is used to identify the components of the mixture. It's very sensitive like gas chromatography, but you can test more substances than gas chromatography. So if we have a look at the chromatogram down on the bottom left, we should note that it's the area under the peak that indicates concentration. So you can see that, oh yeah, this doesn't really match up, does it? So it says 0.253 ppm, but it's only going up to about 154 because we are looking at the area rather than the peak. Now, the peak will indicate concentration, but the area under the peak gives you a more accurate representation. You can see that the least soluble substances are swept out first as well in high performance liquid chromatography. So high performance liquid chromatography provides both a qualitative and a quantitative analysis of the components in a mixture, so that it's getting more and more precise in the measurements. So the size of the peaks are due to the amount of light absorbed by each component, and this can be used to calculate the relative amount of each component in a mixture. So you can see the first peak, caffeine, the second peak, aspartame, so that's what that artificial sweetener. The third peak is benzoic acid, so you can see it's a carboxylic acid with a benzene ring, so benzenoic acid. And here we go, sorbic acid. You can see that we've also got a carboxylic acid there. And what are we going to do? We are looking at benzenoic acid to create a calibration curve. So we can use a HPLC chromatogram along with a calibration curve to determine the concentration of each component. So let's think about calibration curves. So this is one we look at, this is ethanol in wine, but it could be the amount of protein in a substance or some sort of fatty oil. So if you're looking at olive oil or something like that in a substance, so it's important for food as well. So the retention factor or the retention time can be used then to provide information about a particular compound in a mixture. So we can think about pollutants or forensics or drugs or anything like that. So spiking of drinks, or is there enough ethanol in the wine, for example. So let's have a look at this example. So determine the amount of a particular compound in a mixture. The RF or the RT is compared against the standard or known solution. So then we can construct a calibration curve. So we can see here in the bottom left, we've got 4 standards. We've got a standard at 4, at 8, at 12, and at 16. Once we've constructed our, plotted them on a graph, we can then test against an unknown. So if we have a look at, for example, this relative peak of ethanol from an unknown, we can use that to interpolate the amount of ethanol content in the wine, and it would be about 10.5 there. We can also use retention time and qualitative analysis in chromatograms to test for spiking of blood or drinks or whatever. So if we have a look here, we've got a body fluid, and it's been suggested that, hello, we've been spiked with insulin. So let's have a look here. We've got a chromatogram of a sample body fluid, and you test it against a known sample containing insulin, and then if I have a look here, that should be normal. Maybe this one's normal, but have a look here. We can see that there's quite a bit of a difference here. So this is the body fluid spiked with insulin, and you can use this amount to calculate the amount of the substance in the original sample. You can also combine high performance liquid chromatography with mass spectroscopy to detect a wider range and more minute traces of chemicals. So for example, the amount of monounsaturated fats and compared to with saturated fats in substances to determine the quality of oils and olive oils, for example. Okay, are you able to use chromatography or explain how proteins can be analysed by chromatography? When you're happy with that, please work on the mastery questions today.